How is that a question that I answer? People are just.
Okay.
What are you talking about?
The last time we looked at the first fundamental theorem of calculus and then the mean value theorem. Those two aspects allow us to take functions and solve for different values. We focus on being able to find an average, as well as being able to find, using that average, the specific values that average occurs at. Today we're looking at the second fundamental theorem of calculus, which allows us to take a function and change its variable form. And afterwards we'll look at the net change function, which allows us to find out changes in physics.
Yeah.
So, let's look at some example problems. Let's see how they fit together.
Yeah, science.
I didn't know what it was.
Fundamental theorem of calculus is scary.
This morning I told my parents to throw it away because I hate it.
That's right.
Don't you do that like
Yeah, that's why I don't.
The second fundamental theorem of calculus is a surprisingly simple concept. It allows us to take a function and change how it's evaluated by using a different variable. It also allows us to remove the idea of needing a constant and integrate across a variable instead. So, let's take a look at the following integral. Capital F of x is equal to, let's see, integral from 1 to x of t squared over t squared plus 1 dt. Now, we're going to have to use this to determine what f prime is. In other words, the question mark is, what's the derivative of this function? Now, according to the second fundamental theorem of calculus, the idea of the derivative and the integral are designed to be antithetical, designed to be exact opposites. If you take a derivative and integral and put them together, they cancel each other. This works in two techniques. One with the indefinite integrals, where there's no boundaries, and they just cancel each other, and you're done. With a definite integral, this only works if we're doing this back to a variable rather than a constant. So you notice right up here, the big change is you have x involved. Because keep in mind, if we integrate, we're going to find the numerical answer if we have it bounded by two sides. Because we get an area, a value. So then if we take the derivative of a value, we're going to get always an answer of 0. What this will do, and the correct solution for this problem, it takes this equation, it'll cancel the integral of that equation, but switch the variable to its new form. But instead of being with respect to t, what it'll do is it'll take this function and rewrite it in terms of x. Right, so we have the second fundamental theorem of calculus. Again, a definite integral should always produce a single numerical answer, the area. But if we integrate with respect to a variable, when we take the derivative of that function, it'll still be a function that is changing over time. And therefore, we'll still have a value with x in it. So this kind of function, the second fundamental theorem of calculus, looks relatively simple, but the concept behind it is huge. Because again, the integral and the derivative are meant to be opposites of each other. That applies to the indefinite, when we are unbounded on each side, finding the area generating function. And now also with the definites, we actually have a definable value. And note that this does not care what the bottom number is. The bottom number could be 3, could be 50, could be negative 4,003. It doesn't matter. Because that bottom number is going to end up becoming a constant, when we take the derivative of that constant, that bottom number becomes a 0. Let's look at a very simple example of this in action. It showcases how this fundamental theorem works at the very smallest level, and then apply it backwards to verify this works at this level. Let's take a look at a simpler f function. F of x is equal to the integral, give a random number, 5, to x of the following. Let's go with 3. T. D. So what I'm going to do, I'm going to attempt to integrate this function. Before trying to find f prime, I'm going to actually apply the integral. I'm going to get a new function that will have we plugged in x and 5 into that function. And afterwards, we'll look at f prime. So, take this function and we integrate it. 3 over 2 t squared, evaluated from 5 to x. To evaluate it, plug in x, 3 over 2 x squared, minus plugging in 5, 3 over 2 5 squared. Now I could go ahead and find that solution, but I'm just going to recognize that's what f is. So what if I want to know what f prime is? Well, to find f prime, I would need to take the derivative with respect to x of this function of 3 halves x squared minus this number. That number, of course, when I take the derivative, is going to go away. What we left behind is this derivative. The 3 will be multiplied by the 2, becoming 6 divided by 2 is 3x. Meaning, from the beginning, the derivative with respect to x of this function just replaces a variable. Reinforcing the idea of the fundamental theorem of calculus, the idea that the integrals and the derivatives are inherently connected to each other. Whether they are definite integrals or indefinite integrals. Now, if the variable's in the wrong spot, we have to fix this using some of our properties from theorems 4.6, 4.7, 4.8, 4.9. Example. If I have, for instance, f of x equal to the integral from x to 4 of sine of x.
Attention teachers and students, sorry for the interruption. There is a vehicle at the end of the 400 hallway. It's a blue truck, and the alarm is going off. Please take care of that.
So there's a vehicle in the hallway, and they're like, move it.
Yes, clearly they meant for it to be in the hallway.
Okay.
That's how I viewed it.
The
Alright.
problem is that it's going off there, no?
Our job is to find f prime. But to use the fundamental theorem, in fact, it's the second fundamental theorem, x has to be on top.
Yeah.
So what I'm going to do is I'm going to use one of my properties which states that I can flip the order of an integral provided that I negate the integral. So I negate the integral, I flip the order, the inside stays the same.
Yeah, 4.
Oh, 4, thank you. I was totally going to keep going.
Would that make a difference?
Nope, not at all. So now that I want to find f prime, I can take the derivative of this function, use the second fundamental theorem calculus, but I can shortcut it now. Because again, the derivative and the integral are supposed to cancel and change the variable. So f prime would become the derivative with respect to x of this integral which would then become negative integral of sine cosine
Okay.
so the integral of sine is negative cosine, which means the solution here is cosine x. And I don't think if I'm big enough power supply that I can do it.
I don't know, but I'm gonna just bring in mine tomorrow because I know mine works. So,
I also have one extra in my house. I'll bring that too, just in case.
yeah, so
I like it.
that's a troubleshoot, and I already told you that they may need to order a new one, and to go a little bit higher, like a 650.
We'll try first. Sounds good.
Those are the wrong type of partitions. Telling you there, though. It should be NTFS. Alright, so if you change them to NTFS, it should work.
Is there a way to do that from here?
No, I think you gotta do it with your partition. I tried formatting and it wouldn't do it.
That's, yeah. Okay, so I'm probably gonna have to take this hard drive out, plug it into a different system of partition on a different computer.
Right, yeah.
ATFS?
NTFS.
NTFS.
Yeah, NTFS.
I'll try it.
Alright.
Thank you. Sure. Hey, guess what? We get to format and partition hard drives.
Yeah.
Hey. Never mind, I'll do that during people. Okay.
I have nothing else to do now.
Will you shut that down and take the hard drive out
I can.
and attach it to a different computer?
Sure.
That is working?
Yeah.
So we can format it into NTFS?
Yep.
Cool.
Well,
Yay!
Can't you just like use a USB?
I've never done it before. Do you have one?
I will have to learn first. Yeah, you need another.
Log into one of these computers and see if you can get going. Alright, see if we can do it. Alright. Second fundamental theory of calculus. This is by far the easiest part of your homework. Like, once you realize what it does, you can skip a whole bunch of steps. Because again, all it does is it cancels out the integration with the derivative. Make sure you're reading the directions carefully though, because some say to actually find the integration, some say to find f prime. F prime is the ones you're going to cancel and get you the simple solution. The integration is just an integration problem. You're practicing your integration rules. Yes, sir.
Whatever you post to homework, could you also post the solutions? It makes me uneasy not knowing whether or not I.
You know, I hadn't thought about that, but I will do my best. I'll try to take the last 5 minutes to get that done. Okay? Should be a good idea. That's thank you for asking. I hadn't thought of it. Okay. Yeah, so far so good. Yeah. Alright, last piece. For this one, we need the NCT, the net change theorem. The net change theorem looks like any other theorem from what we've talked about so far, where we have an integral and derivative doing work. But what I want to point out here is that this theorem specifically applies to physics problems. And so the f primes in this case are going to be physics ideas. So first we're going to start by reminding ourselves of some simple concepts from physics. If I start with a position function, I can take the derivative of that position function, d dx, to determine the velocity function. So the derivative with respect to x will always determine the new velocity function. Think of it again, derivative represents the change. So the change of position is the velocity. I can take the derivative again to get acceleration. So what's important to remember is if I'm given a position function and it asks me about velocity, what it's saying to do is take a derivative. It's not going to use that in words. It's implying it by the definitions of those two functions and how calculus works. And the third one, again, not very common, but I'll put it because I can. The jerk, the change in acceleration. Now, as a reminder now, I don't know if there was a calculus state, integrals and derivatives are antithetical. They're opposites. So it works in physics too. If I differentiate to move down this list, I integrate to move up this list. So an integral with respect to our two boundaries will tell me the acceleration. Our integral with respect to our two boundaries will tell me the velocity. An integral with respect to velocity will tell me the position. Now to do this, I have two new terms to remind us of from physics. If you have taken a physics class, you might have heard these terms before. They're very similar, but different. Distance versus displacement.
I love how you write with her now.
Thank you.
Yes, ma'am. Could you take the integral of the position?
Yes. It doesn't really tell anything in terms of physics. So let me showcase a variation on this, and I think everybody can learn something from it. Because some cool things happen with these functions, but they also happen to the units. So let's talk physics. In physics, position is defined as, for example, meters. Right? So moving down this list, velocity is defined as meters per second. Acceleration, meters per second squared. Jerk, meters per second cubed. So going up the list, notice how it follows a similar pattern. I start with second cubed on bottom, second squared on bottom, second on bottom, lack of seconds. What would happen if I kept going?
SM.
I get seconds times meters. So if I tried to go one farther up, I get seconds times meters. But what is that? What's meter minute? Like, that's why it's not really talked about, is because we don't really have a use for it. Like, meters per second makes sense because that's how we define velocity, but meter seconds, where they're on the same line, they don't really have it well defined. There isn't one, because it's not used for anything yet. And maybe someday they'll find out that the secret to dark matter was hidden right here the whole time. I don't know. As of right now, there's not really a solid application of meter seconds.
I'm just asking because
No, that's a great question.
if you take an integral of a function and get or something like this, then
What's the equivalent of integrating a position function? Do you find like the area of the position or something? Yeah, it's kind of weird, isn't it? Yes, sir.
You want me to just delete and format all these functions to then use?
Leave them on.
What exactly?
Okay. All right. Physics. Those of you guys who have taken a physics class will remember your concepts from chemistry where they talk about this as well. Displacement versus distance.
Distance is the total amount traveled. Displacement is from point A to point B.
So total traveled?
I think. Maybe I'm scaring something, but I think that's what it was. What?
And what did you say displacement was?
It was just from distance between point A and point B, not just for like the gravity.
So we call this the net change.
Yes, thanks.
Probably why it's called the net change theorem. So let's consider a very simple system, which is common in calculus, a moving particle. So what we're going to consider is this particle, which I'm going to call Blue Boy, or BB. He has 8 friends, but that one's in Star Wars, we don't talk about that. BB. Good jokes. Okay, take a look. This particle, he decides to go on a path. Now this particle, for this particular example, to make it very, very, very simple, this particle is going to be attached to a string. It can only go forwards and backwards. Now, to show this best, I'm going to not show it as a true linear path. I'm going to give it just a little bit of distance. But consider everything to be assumed to be linear. BB decides to travel 4 meters forward. He gets bored, decides that he's going to travel back 6 meters. Yep, it does, doesn't it? And as it's going back forward 5 meters. Now, the big difference between these two numbers is what happens next. The distance traveled will be the sum of these 3 numbers. So 4 plus 6 plus 5. So in this case, we get 15 meters. The displacement would be the net change from the starting place to where they finished. So in this case, they started with 4 forward, they went back 6, so now they're currently at what we could think of as -2. Then they went forward 5, meaning they end up as a positive 3 meters. Big difference between those two numbers. And if you only travel in one direction, these two values are the same. But if you make any kind of change, this is different. I like to think of displacement as football terms. Because when you talk about a football game, if you say the linebacker ran for 5 yards, they don't actually mean 5 yards. It means he only traveled 5 yards forward. He could have, booked it side to side for days and walked 5 yards forward, and he's got 5 yards. The fact that he did all that running doesn't mean anything. It's also why I hate stats in football, because I'm like, I watched that man spend 10 minutes going back and forth and run the field for 20 yards. I'm like, that man worked out. He deserves a raise. Displacement works out. Now the thing is, integration formulas can determine both if you're careful. Here's how. To do so, now I'm going to write this in a very specific way, so make sure to note the two differences between them. In both cases, it starts with this idea. The integral from a to b given f prime dx is equal to f of b minus f of a. What we're going to do now is analyze these in terms of the two functions displacement and distance. So, the standard integral from a to b of f prime of x dx will tell you displacement. The standard integral assumes, in terms of the physics, it's going to give you displacement. And I think about the area function, it did that too, right? It doesn't tell you the total area, it tells you how much is above the axis. To find the distance traveled, we have to make a modification of this formula. And it's a simple modification, but an important one. Here we go. To find the distance, the modification is, so the integral from a to b, now it's an absolute value function. And just like with last time, we'll often have to split this absolute value into multiple components in order to find the displacement versus the distance. Finding the displacement, physics-wise, is easy. Just an integral. Finding the distance, that's a little harder because you have to think of everything as being a positive number. Even though, again, going back to our example, we think of these as positives because we're thinking of them as the particle. So the particle, they went 4, they went 6, they went 5. From outside of the particle's perspective, that doesn't make sense because they went 4 forward, but 6 back. So again, the distance traveled is 15, the net change is 3. So in terms of our formulas, the displacement tells you how much is above or below the axis, the areas. Or in this case, if it's physics, if I'm given a velocity, it'll tell you how much went forward, how much went backwards overall, the displacement. But if we absolutely value the function instead, it'll determine the actual distance it travels. And just like last time, it'll cause us to have a small change in this function. We'll also have to split it apart into multiple pieces. This is where the fun begins. So, let's look at the following. Example. This little diagram, if you plan on taking the AP exam, understanding this is a couple of points by itself. Because some questions will say, hey, here's the position function, find the velocity for me. And if you remember, oh, I just got to take the derivative and now I have the velocity, well, that's an easy problem. If you don't, you're like, what do I do? Uh-oh. And the same goes the other way. If I give you an acceleration function and say, hey, find the velocity, you're going to sit there and go, integrate, there's my answer. So, let's take a look. These ones, if you plan to take the exam, there is a question on this exact topic every year. When people say it's just hard to predict who's going to get an AP exam for typists, one of the questions every year is one of these. Guaranteed. It's a physics question asking the position of a particle. I would put money on it and be confident I'm going to make my money back. Here we go. Remember these two formulas? I'll come back to them in a second. Function. We have a velocity of a particle moving along a straight line. So a particle moving along a straight line. We know the velocity function, v of t, is equal to t squared minus t minus 12. When my time is between 1 and 5. Determine the displacement of the particle and determine the distance traveled by the particle. This will be problems like 97 through 102 and more. We're given velocity, told to find displacement or distance. That means we're given velocity, we're asked to find a position of some kind, we're going to integrate this function. But how we integrate and which one is which matters a lot. So, let's treat this problem one piece at a time. To start with, I want to tackle the easy one, displacement. To find the displacement, I'm going to take this function, I'm going to integrate from 1 to 5 of t squared minus t minus 12. Bring it back to top. Alright, we've been doing integrals for a couple weeks now. Talk to me. What is going to equal this function?
1/3 t cubed minus 1/2 t squared minus 12t.
1/3 t cubed minus 1/2 t squared minus 12t. Evaluate from 1 to 5. What will you next?
Plug in 5 and then plug in 1. Subtract.
Beautiful. Plug in 5. Subtract. Plug in 1. Get our solution. Let's do it. So I do 1/3. 5 cubed minus 1/2. 5 squared minus 12 times 5 minus 1/3. 1 cubed minus 1/2. 1 squared minus 12 times 1. Beautiful. A lot of small math and integration. Okay, one piece at a time. 1/3 5 cubed. 125/3. Minus 1/2 5 squared. 5 halves. Minus 12 times 5.
It's a 3.
Minus.
125 is a 3.
Oh, thank you. Look at you. All right, 1/3 1 squared or 1 cubed. Minus 1/3. Minus 1/2, so it becomes plus 1/2. And then plus 12. Okay. We're going to mix like terms here. So 125/3 minus 1/3 would become 124/3. That would become 41? Question mark? 124/3? 0.3? For now, let's leave it at 124/3. Negative 25/2 plus 1/2. So that becomes negative 24/2. That becomes minus 12. Minus 60 plus 12. Those two are going to cancel. So you end up with 124/3 minus 60. That becomes 180/3. 124/3 minus 180/3 becomes 56/3. That is negative 56/3. In other words, in that time, it ended up thinking of a starting position. Here's my particle. It may have done a lot of moving in between, but eventually it ended up negative 56/3 back. That's the displacement. Okay. By comparison, the other piece, a little tougher. The absolute value version, to find the total distance. Before I do that, questions? Let's do it.
When you get a second, I need the product key. Is it like the education product key? What I thought.
Is one for here.
Okay.
Yeah, I was about to
Let's
say
do it again.
So,
Integration. 1 to 5. The absolute value of t squared minus t minus 12 dt. We did absolute values 2 days ago. We did absolute values yesterday. Let's remind ourselves again. How do we do the absolute value functions? What's our first step? Gotta find a split. Where is this going to fall apart? So I can take that. To do that, I take the inside pieces of this, t squared minus t minus 12, let it equal 0. That's where the split's going to occur. 3? Anywhere else?
it's negative, so it's not in the range. Right, it's 3 negative 4 to make it 0. Or did I mix it up?
I think it's positive.
Positive?
I think so.
Negative t.
Right, you'd have t minus, you'd have t plus 3 and t
right.
minus 4, so it becomes negative 3 and positive 4.
Dang it. Sure. Yeah.
Okay. You had the right numbers.
So
So we take it from 1 to 4 of t squared minus t minus 12 dt plus from 4 to 5 of t squared minus t minus 12 dt. All we really now is figure out what happens to the absolute value symbols. One set's going to change, one set probably is not going to. To do this, I recommend treating it just like we do with the first derivative test. Pick a number in the range and see what happens. This one changes. If we pick a number like 2, 2 squared is 4, minus 2 would be 2, minus 12 would be a negative number. Since it's an absolute value, I want that to become positive. So I take this integral from 1 to 4, I negate everything. So because this answer gives us a negative solution, I have to put a negative into the problem. All right, the other one. If I plug in like 4.5, I get a positive number. I can also just try 5, because again, the boundary points are at -3 and 4. So even though 5 is not in this range, it's just about the same character as 4.5. Some little tricks you can learn. But this one should not change at all. So plus from 4 to 5, t squared minus t minus 12. dt. All right. We just do it one piece at a time. All right. The first integral. How are we going to get this first function? I would shift the negative first. So negative t squared plus t plus 12. Now what?
3 halves plus 1/2 t. Oh, wait, maybe I should actually negative 3 halves t cubed. There we go. Oh god, I'm messing it up again. 1/3. There we go.
There we go.
1/3. Oh my god. There we go.
Add 1 to the power, divide by the new power.
Yes.
Okay?
Plus 1/2 t squared plus 1. Yes. I was going based on.
Evaluated from 1 to 4.
Plug in.
Plus. Okay, this piece. Yeah, there's going to be a lot of duplicate information here. 1/3 t cubed minus 1/2 t squared minus 12t. Beautiful. Let's do it. We will know we've done this correctly if this left-hand piece gives us a positive answer and the right-hand piece gives us a positive answer. Because again, we're doing an absolute value, so everything should end up positive when we're done. Let's do it. First one. Plug it in 4, then plug it in 1. So negative 1/3 4 cubed plus 1/2 4 squared plus 12 times 4. That's the entire first part. Minus, plug in 1. That'd be negative 1/3 times 1 cubed plus 1/2 times 1 squared plus 12 times 1. All right, that is just the first piece. I'm going to solve that, and I'll come back to the second piece. All right, first piece. Okay. Negative 1/3 4 cubed. Negative 64 thirds. 1/2 4 squared. Plus 8. Plus 4 times 12. 48. That's the first piece. Minus the plus 1/3. Distribute the negative. Minus 1/2. Minus 12. Okay, let's do what we can here. So these two together would become 63 over 3, which we turn this into negative 21. 8 and 48, that gives us 56. Minus 12 would give us 44. Minus 1/2, 43.5. So on the left-hand side, we end up with a total of 22.5. Please check my work. So from negative 1 to 4, the amount we traveled from negative 1 to 4 is 22.5. Now which direction? In this case, it's to the left. So they traveled negative 22.5 to the left first. What do they do next? They went to the right. Whatever this is. So do the second piece. Plus All right. Evaluating 5 and 4. Now the next thing is, we've already done 4 once. Use that to help you as much as you can. Okay, so plug in 5. 1/3. 5 cubed. Minus 1/2. 5 squared. Minus 12 times 5. Minus negative 20. Whatever this is. I'm just going to copy those 3 numbers down. Negative 64 over 3 plus 8 plus 48.
Do you know how to get BSOD up?
And we have to simplify. We're done. There's a lot of duplicate work in these. I strongly suggest seeing what you can do to simplify it. Work it a little easier, alright? Otherwise, you get pretty rough. So take every shortcut you can along the way. Alright? We'll continue this topic tomorrow.
Okay.